Okay, so this is from Mrs. Cucci's Pre-Calculus College Now class. Today we are on lesson 2.6, and we're going to be talking about variation and applications. Now, we talked about variation last year with direct and inverse variation, so we're just going to expand on that. Okay, so by the end of this lesson, you're going to be able to find equations of direct variation, inverse variation, and then combined variation given values of variables. We're going to be able to solve applied problems using involving variation as well. Okay, so those are our goals. So if we're talking about direct variation is if a situation gives rise to a linear function, so f of x equals k times x or y equals k times x, where k is that positive constant, we say that we have a direct variation, or that y varies directly as x, or that y is directly proportional to x. The number k is called variation of constant, or constant of variation, as we called it last year. It's also called the constant of proportionality. So again, direct is that y equals k times x. Okay? And that's nothing new. You knew about that last year. So suppose a veterinary assistant earns $10 per hour. In 1 hour, they earn $10. In 2 hours, it's 20. 3 hours, it's 30, and so on and so forth. So this gives rise to a set of ordered pairs. We've got the pair 110, 1 hour, $10, 220, 2 hours, $20, 330, 440, and so on. So whenever a situation produces pairs of numbers in which the ratio is constant, we say that there's a direct variation. Here, the amount earned E varies directly as the time worked T. Okay? So produces a constant ratio. What I mean by that is 1 over 10 is the same thing as 2 over 20, is the same thing as 3 over 30. It all simplifies back to 1/10. So it produces that constant ratio. All right, so we have E equals 10 times T. So the earnings equals $10 per hour. Or using function notation, E of T equals 10 times T. So this equation is an equation of a direct variation. The coefficient is 10, and we call that the variation constant, or constant of variation. In this case, it's the rate of change of the earning with respect to time. Okay, so as time goes on, the earner or the worker earns more money. All right, so we're going to find the variation constant in an equation of a variation in which y varies directly as x when y equals 32 and x equals 2. So we have to think about what we have. We want to come up with an equation, right? So we know we have our basic equation, since it varies directly, of y equals k times x. Now, we're given a value for y, and we're given a value for x. What we want to come up with is the constant of variation, k, and the equation of variation in terms of y and x. Okay? So we know we have to plug in what we know. We know that y is 32, and we know that x is 2. We don't know what k is. We need to figure that out. Okay? So 32 equals 2k. That's very simple to solve. We just simply divide over the 2, and we get 16 equals k. So that's the first part of our question. We've come up with our variation constant. We've got k equals 16. So now if we want to write an equation of variation in which y varies directly as x, we can say that y equals 16, because it's our constant of variation, times x. Okay? So this was part A, find that constant of variation. Part B is to find the equation that goes along with it. And again, this isn't new. You guys have done this before. Okay? Okay, so let's move on to the next page. Water from melting snow. So this is that application piece, right? How are we actually going to use this in real life? So the number of centimeters of water, W, produced from melting snow varies directly as S, the number of centimeters of snow. Meteorologists have found that under certain conditions, 150 centimeters of snow will melt to 16.8 centimeters of water. To how many centimeters of water will 200 centimeters of snow melt under the same conditions? So we have to figure some stuff out, okay? We need to know, since we know we're using y equals k times x, right? It varies directly. We need to know what that value of k is so that we can come up with an appropriate equation. okay? So we start with what's given to us, y and x initially, okay? Says they found that 150 centimeters of snow will melt to 16.8 centimeters of water. So let's say instead of y, we use S for snow. And instead of X, we use W for water. Okay? So now they tell us 150 centimeters of snow. And then K time, and that's going to become 16.8 centimeters of water. So what we need to determine is what my K value is. And we know that we can do that through division. Okay? So 150 divided by 16.8 gives us approximately 8.9. Okay? Approximately 8.9. So, and remember, this is a rate of change. Now, it's going to be centimeters per, pardon me. Sorry about that, I had a tickle in my throat. Okay, so now we want to figure out what if I have 200 centimeters of snow. What does that melt down to for water under those same conditions? So we're using that value of K that we've determined. And instead of having 150, because that's how much snow we had, we're going to be using 200. And our K we know is 8.9. And what we're looking for is how much water that's going to melt down to. So we do the division. 200 divided by 8.9 is going to give us about 22.5. And that's going to be centimeters. Make sure you include your units. Okay? So again, direct variation, you take what you know, you find that constant of variation, and then once you have that constant of variation, you set up your new equation and you solve. All right, let's look at the next page. Let's talk about inverse variation. So inverse variation is when you have a situation that gives rise to a function f of x equals k divided by x, or y equals k over x, where k is positive constant. We say that we have an inverse variation, or that y varies inversely as x, or that y is inversely proportional to x. The number k, again, is called that variation constant, or constant of variation, constant of proportionality. So it's the same kind of idea. You first take your initial x and y, you solve for k, you take k to make a new equation. All right, so let's take a peek. All right, so suppose you have a bus and it's traveling a distance of 20 miles at a speed of 5 miles per hour. Well, the trip is going to take 4 hours if I go 10 miles an hour. It'll take 2 hours if I go 20. It'll take 1 hour at 40, and it's, I guess I'm off here, and it's going to take a half hour at 40 miles per hour. Sorry about that. And so on, okay? So what we do is we plot that information on a graph using speed as the first coordinate and time as the second coordinate to determine this set of ordered pairs. So 5 miles per hour, 4 hours, 10 miles per hour, 2 hours, 20 miles per hour, 1 hour, 40 miles per hour, a half hour, and so on. So whenever a situation produces pairs of numbers in which the product is constant, we say that there is an inverse variation. Okay, so here the product, 5 times 4 is 20, 10 times 2 is 20, 20 times 1 is 20, and 40 times 0.5 is 20. Okay, so that product is constant. So we wind up with this equation, rate times time equals 20, right? That's the same thing as time equals 20 divided by the rate. Or in function notation, time in terms of rate equals 20 over the rate. So this is the equation of an inverse variation. Our constant, or our coefficient 20, that's our variation constant, or constant. Sorry, constant of variation. Okay, so that's going to be our K. All right, so we're going to find the variation constant and an equation of variation in which y varies inversely as x when y is 16 and when x is 0.3. So, keyword varies inversely. You should automatically be writing down y equals k over x. Next, we're going to take what we know. We know y is 16. We know x is 0.3. Okay? So in order to find k, we need to multiply. We're going to do 16 times 0.3, 0.3. And we're going to get a value of 4.8. Okay, so that's the first part. I found my constant of variation. Next, I want to come up with an equation. So again, this is k. My equation becomes y equals 4.8 divided by x. Okay, so let's look at an application. Filling a swimming pool. The time t required to fill a swimming pool varies inversely as the rate of flow r of water into a pool. A tank truck can fill a pool in 90 minutes at a rate of 1,500 liters per minute. How long would it take to fill a pool at a rate of 1,800 liters per minute? Okay, so first thing we need to do is we need to take what we know and figure out our constant of variation. Okay, we know that it's going to take 90 minutes to fill a pool at 1,500 liters per minute. So our first step is to find that k. So we're going to do 90 times 1,500, and we're going to get our constant of variation to be 135,000. Okay. So now we know our constant of variation. The next question is, how long would it take if we're dealing with a rate of 1,800 liters per minute? So this is where liters per minute was prior. So that's where liters per minute needs to be this time as well. So what we're solving for is how long, how many minutes. 135,000 divided by 1,800 gives us 75 minutes. Okay, so that was inverse variation. Where we're going to go from there is combined variation. And this is something new. We haven't talked about this before. Okay, so y varies directly as the nth power of x if there is some positive constant k such that y equals k times x to the nth power. Y varies inversely as the nth power of x if there is some positive constant k such that y equals k over x to the nth. So there's your direct, k times x to the nth, inverse, k divided by x to the nth. Y varies jointly as x and z if there is some positive constant k such that y equals k times x times z. Okay, so these are your three new ones. Okay, I would suggest writing these down on a note card and memorizing them. You do have to know them. I'm not going to give them to you. All right, so there are other types of combined variations as well. For example, if we have a formula for volume, volume of a right circular cylinder, volume equals pi r squared h, in which v, r, and h are variables and pi is your constant. We said that v varies jointly as h and the square of r in this formula. Pi is the variation constant. Okay, so there are other ways to look at this as well. So we're going to find an equation of variation in which y varies directly as the square of x and y equals 12 when x equals 2. Okay, so we're going to have to kind of pull this apart. So we're saying that it varies directly with the square, right? So the first thing you should be writing down is y equals k times x squared. Okay, and that was given to us, right? We know that we have to memorize that. So the next thing we're going to do is we're going to plug in what we know. Okay, we know y is 12. We don't know what k is. And we know x is 2. In this case, we need to square it. So this is the same thing as 12 equals 4k, or k equals 3. Okay, so now we know k. So in order to write an equation of variation, we're going to plug in that value of k. So we get y equals 3x squared. And that's your equation. So it's not difficult to use, it's just a little bit different from what we're used to seeing. Okay? So let's try the next one. We're going to find an equation of variation in which y varies jointly as x and z. And y equals 42 when x equals 2 and z equals 3. So varies jointly, you got to have your equation y equals kxz. Like always, what we're looking for is k. We know y is 42. We don't know k. We know x is 2. And we know z is 3. Okay? So we get 42 equals 6k. And then when we divide that over, we get k to equal 7. So to write your equation, we get y equals 7xz. So again, not difficult to use. They're just different from what you're used to seeing. Okay, find an equation of variation in which y varies jointly as x and z and inversely as the square of w. And y equals 105 when x equals 3, z equals 20, and w equals 2. All right, so we have to kind of pull this apart little by little. Okay, so this one's a little bit different, all right? We're going to have y equals k times, now this is where it gets tricky. It varies jointly, which is why we have the y equals k times. But now it varies inversely with the square of w. Okay, jointly means we have to have that x and z, and then inversely means we have to have that divided by the square. So we've got xz in my numerator, and then the denominator I have my y squared. Okay, so it varies jointly. We've got our yxz inversely divided by the square of w. So if we can come up with the equation, it's simple to use after that. We know that y is 105. We don't know k. We know that x is 3 and z is 20 and w is 2. Okay, so when we simplify that out, we get 105 equals 15k, or k equals 7. Okay, so I know that the original equation is tricky. It just takes a little practice on how to figure that out. So now that we have k, what we can do is we can set up our equation, right? Got y equals 7 times, oops, my apologies, xz over w squared. Now you can write it like that, or you can write it like this. Both ways are correct. Okay, so a lot of application problems deal with combining two different ones, direct and joint, whatever it may be. Okay, so you do have to kind of get used to creating things like this from a problem. Okay, so let's look at an application problem. Volume of a tree. The volume of wood V in a tree varies jointly as the height h and the square girth g. Pardon me. If the volume of a redwood tree is 216 meters cubed, when the height is 30 meters and the girth is 1.5 meters, what is the height of a tree whose volume is 960 meters cubed and whose girth is 2 meters? Okay, so let's think about what we have here. It's saying that it varies jointly with the square, right? Varies jointly with the square. So what we're dealing with here is it varies jointly, which means I have to have that, x, y and z. We're not going to use those variables, but x, y, z is what we want. And with the square of the girth, okay? So volume we always say is v. That's going to equal my constant. We always have to have that, times the height, h, times the girth of the tree, but we want that squared. Okay? It says the tree varies jointly as the height and the square of the girth. Okay, square of the girth. Girth means how far it is around. That's what girth means, if you didn't know. So we know a bunch of this information. We know our volume is 216 meters cubed, and we don't know K. We know that my height is 30, and that my girth is 1.5, and in this case, squared. Okay. So what that is we have 216 equals K times 67.5 when you do the math there. I'm sorry, this is supposed to be 1.5. Must have hit 0 instead. Okay, so when we divide this out, we get K equals 3.2. So we have our constant of variation now, okay? So what we're going to do now is you're going to use that constant of variation to create my new equation, right? We've got volume equals 3.2, which is my constant of variation, h, the height, times the girth squared. Okay, so there's my new equation. We're going to use that to answer the question. It's saying, what is the height of a tree? So we're looking for h, whose volume is 960 and whose girth is 2. Okay, volume is 960. We don't know the height, and we know the girth is 2 squared in this case, so we can say 4 because we know how to do that. Okay, so we get 960 equals 12.8 times the height. And when we divide that over, we get a height of 75. And that, of course, is in meters. Okay, so that is inverse, direct, and joint variation. So I know I went over. I apologize. I will see you guys tomorrow. Bye.